As scientific tools have advanced, microbiologists have demanded better ways to understand DNA. Differential geometers, such as myself, are among those who have attempted to answer this call, and our goal was to build a mathematical model that could be used to represent DNA. As a pure mathematician, my focus has been on the mathematical aspects of such a model, rather than the direct applications. Now, despite what your high school textbooks may have illustrated, DNA actually spends the majority of its time in a circular form, that is, having no loose ends. As you can see here, a mathematical knot is a closed curve in three-dimensional space. This makes knots a very natural starting point in our attempt to model DNA. However, it's important here to realize that DNA is not really a perfectly smooth piece of string or wire, and therefore our use of knots as a model falls somewhat short, as they do not account for DNA's non-uniformity. Therefore, we propose the idea of a weight function. A weight function gives us the ability to match DNA's varying thickness by specifying values along the length of a knot. Intuitively, we like to think of these weighted knots as being a piece of wire along which some sort of gel representing the weight has been spread. Here I'm using red to represent the heavier areas and blue to represent the lighter ones. Of course, we would like to be able to compare weighted knots, but here a picture can only tell us so much. In a way, it's like shopping for a car. Photographs tell you part of what you would like to know, but ultimately you want some quantitative information like fuel efficiency or horsepower. This is where mathematicians have designed a variety of knot-specific statistics called knot energies. The Mobius energy is one of the most important knot energies. Defined in the early 1990s, the Mobius energy is roughly correlated to the complexity of the knot and is defined through a rather complicated formula. Part of our work was generalizing this formula so that it also allowed weighted knots. And you can see here, for example, this weighted trefoil has a Mobius energy of about 560. Returning now, though, to the car analogy, it's clear that if you change the car's tires, it could affect its fuel efficiency, but changing something like its paint color would not. We want to ask similar questions about the Mobius energy, specifically, how will adjustments in our weighted knot affect the Mobius energy? And that's been the focus of much of our research. One of the simplest variations we've considered is called the equitotal variation. Here you can see we've kept the core curves the same, we've kept the total weight the same, but we've allowed the weight's distribution to change. We've found that when you pile all the weight in one spot, it actually causes the energy to fall somewhat, whereas piling it in multiple places causes the opposite effect. The weight rises, or the energy rises. Whereas allowing it to spread out rather evenly, unsurprisingly, results in a rather average-looking energy value. Of course, there's many other variations we've considered that we don't have time to discuss today, but ultimately the hope is that someday this research could build a model that would contribute to our understanding of DNA.